Hello class, and we are going to look at problems, or equilibrium problems, where we have more going on than we've been dealing with before. So a classic type of problem that increases the level of challenge, mostly by increasing the level of what we need to be paying attention to, are ladders leaning against walls. For all problems that we're going to do that involve more work, that involve more reasoning, the same three steps that we've been going for are going to be applying. Make your free body diagram, choose a good fulcrum, one that eliminates some of the unknowns, and use your two equilibrium conditions to make relationships. If you remember, your two equilibrium relationships are your translational equilibrium, so this is where your F net for your both x and your y is equal to 0, and your rotational equilibrium where the net torque is equal to 0. Balancing these two equilibrium conditions with a good free body diagram is going to be the way to do every single one of these problems. So let's start with our first problem, the one that I've labeled the warm-up problem. There's a uniform ladder, so that's telling us that it's an even mass, and we can take the center, we can take the force of gravity on that ladder at its center of mass, where the mass is 40 kilograms, the length is 10 meters, and it's leaning against a smooth vertical wall. When we use the word smooth, that means frictionless, so we don't have to worry about any friction on the wall. So that's nice. Now there's a person who's been climbing up the ladder, and they are an 80 kilogram person, and they're going to stand a distance where x is 7, or where if we take a look at our diagram, x is the distance from the bottom of the ladder. The foot of the ladder is distance d, 1.2 meters from the bottom of the wall, and what force is exerted by the wall from the ladder? So that's the normal force exerted by the wall on the ladder. That's what we have labeled as S here. You can see that all the forces are already labeled. Force S, force mg, that's the gravity of the person. Little mg, that's the gravity of the ladder. Force R, that's the normal force from the floor, keeping it from falling in. And this script F is the friction force. So there are two forces where there are two questions actually. What is the force exerted by the wall on the ladder? So we're trying to find S. And then what is the normal force exerted by the floor on the ladder? So we're trying to find R here. In this case, taking a look, we have a lot going on. There's a lot of different values. We can work this out. We just need to take a little bit of time. Some things for us to check is the length is 10 meters. The d distance is 1.2 meters. So even though we weren't given this angle, we'd be able to find out that angle just by looking at a little triangle. This is a 10 meter and this is 1.2 meters. We'd find this angle because I'd be looking at my hypotenuse and my adjacent. So cosine of this angle is my adjacent side over my hypotenuse. Or I can take my arc cos, 1.2 over 10, and let's grab our calculator and figure this out. 1.2 divided by 10, and I'm going to take the arc cosine of that. Looks like it's 83.1 degrees. Theta is equal to 83.1 degrees. And look at that, you might be like, wow, this diagram is very much not to scale, and you'd be absolutely correct. But that's okay. What matters is clarity. What matters is having a very clear set of what's going on. So let's try to figure our way out. We have mg, this is the force of the person. Let's put down any value we can. This was 80, the person's 80 kilograms times 9.8. Oh, I closed my calculator, my mistake. 80 times 9.8. So that's 784 newtons right there. 784 newtons right there. This little mg is the ladder, so that's 40 times 9.8, or 392 newtons. 392 newtons. And do we know the force of friction? Well, the force of friction is the coefficient of friction multiplied by the normal force. Do we know the normal force? I don't know. Maybe. Maybe not. You know what we haven't done is we should probably check our equilibrium conditions. So I've got my translation and I've got my rotation. And I'm going to write down both of these. I'm going to split my page so I can pay attention to both of them at the same time, see if this gives me any information. For translation, we are dealing with an x and y axis as well. So F net x equals, and I'm going to look at all of my x things. What is going in x? I notice that the friction is in x, so I have friction going one way. And then the normal force on the wall is actually going the opposite way. F minus S. And then my net force Y equals, and I've got gravity of the person heading down and gravity of the ladder heading down. Those are both down. And the only other up is the normal force on the floor. Now I know this is 0. I don't know my friction force, but I do know that my friction force is the coefficient of friction multiplied by the normal force on the floor, because that's on the floor. So this mu times r minus, and s I don't know. R and s are actually the ones that we don't know at all. But on my y side, we have big mg. That's 784. And we have little mg. That's 392. And, oh, sorry everybody, that's not a plus. R is up, and the other two are down. It's negative of them. It's subtracting them. Well, look at that. I don't know about you, but this is so convenient. R is whatever these values are, right? R is just the addition of these two. So that's 6, 7, carry the 1, 11, 76 newtons. We actually already got the normal force exerted by the floor just by using our translation, just by using our net force, because if this is in equilibrium, it's not going down and it's not going up. That means my up-down gives us everything. That's very, very convenient. 1176 newtons. Do we have such luck with our normal force on the wall? Well, taking a look here, hey, look at this F net x. I can use this, substitute it in. 0 is equal to the coefficient multiplied by 1176 minus S. If I know the coefficient of friction, this problem is solved, and I didn't even need to look at a rotation. Let's see, uniform ladder, smooth wall, not smooth floor, so no, distance ladder, measure foot of the ladder. Oh. Seems in this problem we're not given any coefficient of friction. This force of friction is going to remain an unknown for us. We're stuck. We're stuck if we were only using translation, but we can still use rotations. And in this case, what do I want? I want this S, what's unknown, this F, so I'm going to choose a fulcrum right here. That's my fulcrum, because that will mean whatever torque that's happening for F is eliminated. It's not doing anything. And so now I've got this beam. It looks like my two gravities, if I were to try to see what they're doing, is they're pushing down this way. That's a counterclockwise, so my two gravities are counterclockwise while my normal force is clockwise. But the trick here is neither of these gravities nor my normal force are actually perpendicular to the beam. We have to deal with finding the perpendicular person gravity, the perpendicular ladder gravity, and the perpendicular wall normal force. These are the ones that are going to do it. So let's take a look. Rotation. T net. The torque caused by the wall is clockwise. And then it has two torques working against it. The torque caused by the person, we'll call that big M, and the torque caused by the ladder, little m. Okay, now here's the real trick. Here's where the real work is you need to find out where does this angle, this 83.1 degrees, go. 83.1 degrees here, 83.1 degrees here, 83.1 degrees here, and 83.1 degrees is this angle. So if I wanted to find out S, this is a perpendicular component to that. This is an 83.1. This is going to be 6.9 degrees because it's complementary. 6.9 and 83.1 makes 90. So that's going to give me a little bit of flack there. Let's see, we got 0 net torque is equal to torque S is force S multiplied by, and see how my inside angle is 6.9, cosine of 6.9 degrees multiplied by, because remember it's always F perpendicular times D. How far is S from our fulcrum? If the fulcrum's down here, it's the total length. The total length is 10 meters. We subtract the force caused by big mass, that's 784. 784 multiplied by the cosine of 83.1 degrees, and then we're going to multiply by how far is it away from the fulcrum? It is distance x, and if we remember looking in the problem, it says in the word problem it says that they are 7 meters up the ladder, so there's 7 minus, and then it's 392 cosine 83.1 degrees multiplied by, where's the center of mass? It's in the center. 10-meter ladder means the center of mass is 5 meters up. And that might look a little fussy, but those are all just a bunch of numbers. So I'm just going to combine those. I'm just going to calculate those out. Let's grab my calculator. 784 times 83. The cosine of 83.1. And then I'm going to multiply that by 7. We're going to subtract 392. That's multiplied by the cosine of 83.1. And then we multiply that by 5. Equals 423.8. I'll just call it 424. So 0 is equal to 424. I'm just going to do this cos 6.9 times 10. That's 9.92. So this is 9.92 S's is equal to 424. S is equal to, this is pretty easy math from here. 424 divided by 9.92 equals, that's 42.7. 42.7 newtons. We've just found S, S is 42.7 newtons. There we go. And actually, now that we have S, if we really wanted, we could even find the coefficient of friction of the coefficient of friction, since we now have S. But that wasn't actually a problem written in there, so that's okay. Hopefully this wasn't so crazy. As you can see, what are the things that help me do this is, one, having a very clear diagram where I can label all of my forces and I have enough space for it. That's why I don't care if it's to scale. That's why I care if it's visible, right? Why I can use space for it. So make your diagrams nice and big. Don't do those teeny diagrams. Make them nice and big so you have space to write down all the things that you need. And then, once you got your diagram, split your two types of equilibrium. This is translational equilibrium and rotational equilibrium. Use your net forces, use your net torques, and fill out until you fill out until you get stuck somewhere, and then move on to the next thing. So I started using translational equilibrium, and I filled out and got some of the things I needed, and then I got stuck, so I moved over to rotational equilibrium, chose a fulcrum to find the pieces that I was stuck at, and then use that, found the pieces, and then I can bring it back. I would actually always recommend starting with translational equilibrium, because you don't need to choose a fulcrum there. It's just net forces. Start there and then see what's missing. What am I stuck on in your translational equilibrium? And then use that information to choose a smart fulcrum for your rotational equilibrium. So that's what I would always recommend. I would recommend start with translation and then move into rotation after. And if translation ends up not getting you anything, well, you just lost you just lost a minute or two. Hopefully it's not that important. I hope that this problem seems okay, because this is the warm-up. It's time for us to take a look at the real challenge problem. We have a ladder, it's linked against a wall, and there's a coefficient of static friction that we're calling mu w between the ladder and the wall, and the coefficient of static friction we're calling mu f between the ladder and the wall. Or between the ladder and the floor, sorry. So ladder and wall, mu w, 0.3, and the ladder and floor, mu f, 0.4. The center of mass in the ladder is in the middle, so we're saying this is a uniform ladder. Find the minimum angle that the ladder can form with the floor and not slip down. This problem, if you start thinking about it and you start trying to draw what's going on, so I've got, let's see, I've got a wall and and I've got a floor, and I've got myself a ladder, which I'm going to do in purple. There we go. I've got a wall, I've got a floor, and I have my ladder. Something that's not given is I didn't actually give what the length of the ladder is. How long is that? If you don't know, call it L. You have to give it a variable. Something else that's missing is the mass. You know the force of gravity is going to be acting this way, force of gravity, and that's just going to be mass times g. M is missing. It's not actually given here. Well, that's a real conundrum. We've got a lot to work on. Well, guess there's no place to start but the beginning. Let's start by including all forces that are on this. there's probably going to be some normal force between the floor. I probably want to give it a nice clear name so I don't mix anything up. I'm going to call it F. I'm going to stick with this, FR, floor, R for floor. And if you wonder why R for floor, is because FF is already taken for friction. For example, if I let this ladder go, it would slide, the top sliding down and the bottom sliding across the floor this way. So there's a force of friction along the bottom, keeping it from going. Pardon me, F friction from the floor. So I'm going to call it FFR, friction from the floor. Is there a normal force from the wall? Yes, it is. Yes, there is. Normal force of the wall. I'm actually going to call it F. W. Pardon me. And there's friction on the wall. If this ladder was to let slip, it would slide down the wall, which means friction must be pointed upward. What's a color I haven't used? Pink. I haven't used pink. So force, friction, wall. Are there any other forces? Nobody's climbing it, so we're actually okay. Now, what's tricky about this is, one, we have absolutely no idea what this angle could be, and in fact, finding that angle is our purpose. That's our task. So we need to find some way to figure this out. And the only thing we know are these coefficients. We know coefficient of the wall. Mu W is 0.3, and we know the coefficient of the floor, mu floor, is 0.4. Those are the only numbers given. It's a real conundrum, a pickle perhaps. Well, what I'm going to do, I'm going to give myself a little more space, so I'm going to set up my two equilibrium conditions, my translation and my rotation equilibrium conditions. All right, translation over here, rotation over here, translation, rotation, set up X, set up Y, F net X is equal to, what's going X? Looks like the normal force of the wall is X, and it looks like friction of the floor is in the X. And in my Y, F net Y is equal to, looks like gravity is going down, but the normal force from the floor is going up, and the friction from the wall is going up. Okay. I said we should start with translation first. Let's see what we can figure it out. I know net force is 0. F wall, there's no formula for the force from the wall, so that's not. But how do we find friction? Friction is always the coefficient multiplied by the relevant normal force. What's the coefficient of friction on the floor? 0.4. And the relevant normal force is force R. 0.4 force R. So force wall is equal to 0.4 force floor. That's not an answer yet, but that's something. What yet? We don't know. maybe y will help us out. F net y is 0. This is 9.8 times m, right? mg minus Fr. Fr, there's no formula for Fr. But wait, force friction wall. Friction is coefficient by the appropriate normal force. The friction of the wall is 0.3 times the wall normal force. 0.3 times the wall normal force. And here, we're kind of starting to get somewhere, because we know the force friction wall is 0.4 Fr, and we'd be able to do some substitution here, right? We can get both of these in terms of Fr and solve for Fr, except we still have that unknown of the mass. It's not going to get us the force R. And actually, that doesn't get us anything with the angles that we're dealing with. This seems to be a puzzle. We seem to be stuck. So if this isn't going to get us the things that we need, what do? We move over to rotation. So when I'm dealing with rotation, is I want to set a fulcrum that gets rid of some unknowns. Looking at my translation, this is actually going to help me figure out. Notice I have Fw in terms of Fr. I can substitute Fw in here, and so I can have 0 is equal to 9.8 m minus Fr minus 0.3 times 0.4 Fr. And so that's just 9.8 m is equal to 0.3 times 0.4 is going to be 0.12. So that's going to be 1.12 FRs. And that's 9.8 m. 9.8 m is equal to 1.12 FRs. M and FR are our variables here. So if I make my system so that I have FR, and if I have FR, then that's what I want. So take a look, where can I put a fulcrum that'll get rid of some unknowns, as many unknowns as possible, but keep FR? I don't want to put it here. If I put it here, I get rid of FR. FR is the thing that I can substitute in. So what do I want to do? I want to put my fulcrum up here to get rid of the W's. Now I don't have to worry about any of this nonsense, any of these W nonsenses. And that's going to be what helps me out. Let's find out what we have. Gravity is pulling it in a clockwise fashion, right? Gravity pulls it that way, clockwise fashion, and the friction also pulls it that way in our clockwise fashion. So let's set those up. Gravity, there's perpendicular gravity, and friction. There's perpendicular friction. You know, I'm going to remove my label of FFR, FFR, so it's not in the way of my diagram. This FR is going in the opposite direction, or the counterclockwise direction, and we can see it'll be pointed up that way. So let's set up my equation. I've got my two clockwise ones, so this would be torque caused by gravity and torque caused by friction R, both doing clockwise work, and then the counterclockwise one is torque caused by regular R, or floor force. That's 0. I know how to get gravity. That's just 9.8 m times, where does this angle go? This angle theta goes in right here, so that's going to be cosine of theta. Times, how far is this? Is it half of the length away? Because it's the center of mass, so that's why it's L/2. There's my force times d. Time to get the friction one. Force, wait, friction, we already got friction. Friction is 0.4, the coefficient of friction, times the normal force. Now, hold the phone. If this is theta, and the purple is perpendicular to our green, then that means this is 90 minus theta. Or it just means that this opposite angle is the same thing as theta here. So my perpendicular, notice how it's opposite? I need to be using sine theta. And it's going to be multiplied by, how far away is it? It is L away. So it is L distance away. And our last one, minus TR, that's just FR times the, you see that's, wait a minute, that's if that's theta, that means this is 90 minus theta, which means this is theta again. FR times cosine of theta times its distance L away as well. Now this looks a little unnerving. There's a lot going on here, but it's not so bad. First off, let's see what different variables we have. We have m, we have theta, which is good, we want theta, and we have L. We have FR and theta and L, and FR and theta and L. Every term has these variables. Now the theta is the one that we want to deal with. We're going to keep that there for a second, and we're going to hold on to it, and we're going to just take a moment and take stock. FR and M are the ones that we don't mix. But there's work that we've done earlier that'll save us. See how 9.8 M is 1.12 FRs? And this is 9.8 M's? So let's just substitute all of 9.8 M's with this 1.12 FRs. So I'm going to have 0 is equal to, instead of 9.8 M, it's 1.12 FRs. That was sloppy. FRs multiplied by cos theta multiplied by theta over 2, or sorry, L over 2 plus 0.4 FRs multiplied by sine theta times L minus FR cos theta times L. And this tidies things up a little bit. This tidies things up actually a fair bit. What I can see now is I see every term has FR, 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 and every term has L, L, L. If every term has those, we can factor them out. 0 is equal to FR times L, and what am I left with? I'm left with 1.12 over 2, which, you know what, 1.12 over 2, we can do that. That's just 0.56. 0.56. 0.56 cosine theta plus 0.4 sine theta minus cosine theta. And you're like, okay, this is something. Just to make life easier, what would happen if I divided both terms by FR over L? Cancels out, and 0 over FR over L is still 0. Awesome. We get to, because they are part of every term, we get to factor them out and eliminate them. Here, I can actually make like terms. 0.56 minus 1 cos theta. So I'm actually have 0.4 sine theta minus 0.44 cos theta. And if you're feeling a little stuck here, this is where it's helpful to know our identities. Notice how we're dealing with a sine and a cos. Sine and a cos here. Let's move that cos to the other side. 0.44 cos theta is equal to 0.4 sine theta. Here's where we use our identity. Remember how sine divided by cosine is equal to tangent? So if I divided both sides by cosine theta, I can eliminate this cosine theta, and this sine over cos can become tangent. 0.44 is equal to 0.4 tangent theta, which means 0.44 over 0.4 is equal to tangent theta, and theta is just going to be the arctan of 0.44 over 0.4. .7 degrees. And even though it seemed like we didn't have nearly enough information, if we use our two conditions of equilibrium, we can make it work. So let's just recap, because this seems like a lot. Start off with a nice clear diagram, labeled everything as clear as we could. We then created our translation, our translation equilibrium conditions where our net forces were 0. We tried to break things down in as much detail as we could. Instead of force friction, it's coefficient times normal force. So we were able to put those in. Instead of gravity, it's 9.8 times m, coefficient times normal force. And we broke these down and we used the relationship between them. We used the relationship between them to end up, we used this relationship between them here and here to end up isolating for two sets of variables. This gave us a clue on what we should be doing next. This gave us a clue with our rotation where our fulcrum should be. We chose a fulcrum that allowed us to use that information to get this information, to put down our net torque equation, find out the variables we had, do a substitution, factor out common terms, and then look for your any identities if angles are what you're looking for. I know that this might seem a little advanced, but it is using our same 3 steps that we've been doing before. Clear diagram, setting up our equilibrium conditions, and choosing a smart fulcrum. If you practice this, if you work on these steps, these problems, no matter how intimidating they might be, no matter how different they are, become more approachable. There are some practice problems I'd like you to give a go, and there's a practice quiz that looks a bit different from the ones that you've been doing before. You have to use outside information. You have to use some outside knowledge, or you have to be very aware of the physical nature of what's happening in the system, what forces are acting, and what direction they'll always be applying. So I want you to practice that, work with your teammates and your other classmates to try to figure out these things. You will be getting quizzed with questions that are similar in style to this one on the practice quiz. So while it might look crazy now, it's up to you to work together and find them out. Thanks, everybody. Have a good day.